Hello everyone. In the last couple of lectures, I have given some basic ideas about the quantum mechanics. And in continuation of the same, today I am going to discuss on the famous Heisenberg's uncertainty principle. So let us start with the uncertainty principle. To begin with, the Broglie proposed that a moving body must be regarded as the Broglie wave group and not as a localized entity. It means the moment we associate a wave group with a moving particle, we introduce an inherent uncertainty in the position of the particle. Thus, there is a fundamental limit to the accuracy with which we can measure its particle properties. And this is what all is about the uncertainty principle. That is, we are associating a wave with a moving particle, and therefore the position of the particle becomes uncertain, at least to the extent of the size or the spread of the wave. Now here we have two such the Broglie wave groups. The location of the particle may be anywhere within the groups. Here we have one wave group, and here we have another wave group associated with two such moving particles. Now, if the group is very wide, like for example this one, it allows better wavelength estimate, but certainly the location of the particle becomes uncertain. However, if the group is very narrow like this one, the position of the particle is readily found, but the wavelength is difficult to measure. Then the question is, how do we measure the momentum of a particle? And the standard procedure is, any measurement of the momentum of the particle can be done by letting it interact with an external particle or radiation, that is, by letting it interact with some external agent. In making the measurement of momentum, what we do? We are going to disturb the position of the particle. That is, simultaneously we are not able to measure momentum and position with accuracy. The very nature of the wave group allows us to relate the inherent uncertainty delta x in the measurement of a particle position with the inherent uncertainty delta p in the simultaneous measurement of its momentum. So now the question is, how do we represent a wave group? Because we are assuming that we have to associate a wave group with a moving particle, the Broglie wave or the matter wave. Then how such wave group should be represented? Question is, can a sinusoidal wave represent a wave group? For example, this one. Now, a sinusoidal wave extends from minus infinity to plus infinity. But a particle is a localized entity. Therefore, with a moving particle, if we associate a wave, the spread of the wave must be limited and finite, and it cannot spread from minus infinity to plus infinity. So the representation of a wave group by a sinusoidal wave is certainly ruled out. Then how can we represent a wave group? Answer is, the simplest example of the wave group formation is by the superposition of two wave trains, slightly different in angular frequency omega and propagation constant k. They superimpose to give a series of groups. Like we have psi 1 is equal to a cos omega t minus kx, and psi 2 is equal to a cos omega plus delta omega t minus k plus delta k x. That is, omega has a difference of delta omega from this wave, and k has a difference of delta k from this wave. So on superposition, psi is equal to psi 1 plus psi 2, we have this. That is, psi is equal to 2a cos omega t minus kx and cos delta omega by 2 into t minus delta k by 2 t. That means, you see, after superposition, what we have is the frequency of the two waves that we have seen, that remains almost the same. But certainly the amplitude is modulated, and the amplitude becomes twice a cos delta omega by 2t minus delta k by 2t. And this gives the basically the delta omega is the frequency of the modulated wave, and delta omega by 2 is the frequency of the modulated wave, and delta k by 2 is the propagation constant of the modulated wave. Like for example, here we have this is what we have as psi 1, this is psi 2, both are different in omega only slightly, and the result of superposition of the two is psi is equal to psi 1 plus psi 2, that is this one. So this frequency you can see is almost the same, almost the average of the two frequencies, but here the envelope is the modulated wave that we are getting, and this is what gives the wave group. This is what we call the wave group. And if we remember, then this phenomenon is more or less the superposition of the two waves shown over here having slightly different frequency is almost the same that we had seen in the beats phenomenon of sound waves. There also we had two such waves superposing on each other, slightly differing in frequency, and the amplitude or the intensity of the wave had got modulated, and their plot would be almost the similar as this one. So this resembles the beats phenomenon in the sound wave. Now let us see there is next one, that is we have, let us consider actually the superposition of two such waves will give us a series of such packets or the wave groups. If you want a single such packet, then the superposition should be among infinite number of such waves, each one differing from each other in frequency only slightly, in propagation constant only slightly. So one such wave group shown over here, like for example from here to here, will represent a wave packet or a wave group associated with a moving particle. So we take from here to here lambda m, that is the modulated wavelength of the result of superposition of the two waves. Then this is lambda m upon 2, that is the half of the wavelength of the two. Now the particle will be located, if this is the wave group associated with the particle, then the particle may be located from here to here, that is anywhere. So we can say that the uncertainty in the position of the particle can be to a maximum of lambda m upon 2. So we say that uncertainty in the position of the particle delta x is equal to lambda m upon 2. The width of each group is equal to half of the wavelength lambda m of the modulation. This width may be assumed to be of the same order of inherent uncertainty delta x in the position of the group. The modulation wavelength and propagation constant are related as following. You can see lambda m is equal to 2 pi by k, and that is the standard relation. Lambda is equal to 2 pi by k. Now, however, the propagation constant of the modulation may be written as we have just not seen. It was half delta k. So km is equal to half delta k. So lambda m over here is twice pi upon this half delta k, and delta x, if delta x that was lambda m by 2, that becomes delta x is equal to twice pi by delta k. As the waves that constitute the wave group are a result of superposition of waves of propagation constants k and k plus delta k, even the most accurate measurement of k cannot avoid an uncertainty of delta k. And therefore, delta k is equal to, from the above expression here, delta k is equal to twice pi upon delta x. The Broglie wavelength of the particle having momentum p is given by lambda is equal to h by p, a famous relation. The propagation constant corresponding to this wavelength is k is equal to twice pi by lambda, and put lambda from the above expression, so k is equal to twice pi p upon h. Thus, the uncertainty of delta k in k results in the uncertainty in the momentum by delta p. That is, delta p is equal to h delta k upon twice pi from the above relation. So delta p is equal to h by delta x. So delta p delta x is simply h. Of course, a more accurate calculation will show delta P, delta X is greater than equal to H cross. Now mind it, here we have the symbol greater than equal to symbol is there. Now the equality sign will stand for the irreducible minimum in the uncertainty, that the uncertainty cannot be less than that, and this is inherent in the system. Just because we have associated a wave group with a particle, the uncertainty becomes inherent in the system itself. So this is an irreducible minimum. This uncertainty is irreducible. The uncertainty will not go below this. So equality sign is for that. Now, any measurement process, any error in the measurement process that is added will only increase the uncertainty. So therefore, we have the greater than. So the uncertainty can be either equal to or greater than H cross, but certainly not less than that. Now let us consider another frame, that is energy time uncertainty. In this case, we try to measure the energy emitted sometime during the time interval delta t when an atom de-excites. When we give energy to the atom, its electrons go from the ground state to the excited state. They stay there for some time, and when they come back from the excited state to the ground state, they emit photon. So this time interval that the electron stays in the excited state is very small. So the time available is very short. Hence, this limits the accuracy with which we can determine the frequency nu of the electromagnetic waves being emitted. Now let us assume here that the minimum uncertainty in the number of waves we can count in a wave group is one wave, and it's not a fraction. Since the frequency of the wave is equal to the number of them we count divided by the time interval, the uncertainty delta nu in the frequency measurement is delta nu is equal to 1 by delta t. So the corresponding energy uncertainty is delta E is equal to H delta E. And delta E is equal to H by delta T. Thus, delta E delta T is equal to H. A more realistic calculation will show delta E delta T greater than H cross, and here the greater than equal to sign has the same meaning as explained earlier, that equality is for the inherent uncertainty below which it cannot go, and greater sign is any uncertainty added because of the error in the measurement process. Now consider, for example, the radiation of light coming from an excited atom. The atom divests itself of its excess energy by emitting one or more photons, as we have seen. The average time spent in the excited state is 10 to the power of minus 8 seconds. Thus, the photon energy is uncertain by an amount delta E equals to H cross by delta T. Put the value of H cross, put the value of delta T as 10 to the power of minus 8 seconds, then the uncertainty in the energy is 1.1 into 10 to the power of minus 24 joule. And the frequency of the light therefore is uncertain by delta nu is equal to delta E by H, and which comes out to be 1.6 into 10 to the power of 7 cycles per second. This is the irreducible limit to the accuracy with which we can determine the frequency of radiation emitted by an atom, and any error that we commit in the measurement will add this one, and this uncertainty will become more. Thus, the uncertainty statement for momentum position is given by delta P delta X greater than equal to H cross. Similar uncertainty statements for angular momentum, angular displacement, and energy time are given delta L delta theta greater than equal to H cross, delta E delta T greater than equal to H cross. Next, one more problem that is a very common problem that is always discussed in a classroom situation is that, does an electron reside inside a nucleus? If it doesn't, why it doesn't reside inside the nucleus? Now we will presume initially, let us presume that the electron resides inside the nucleus. So let us take the radius of the nucleus as 10 to the power of minus 14 meter. Naturally, the uncertainty in the position of the electron may be assumed to be of the same order, that is 10 to the power of minus 14 meter. The corresponding uncertainty in the value of momentum will be by the same relation, delta P greater than equal to h cross by delta x. Now h cross is known, and put delta x is as 10 to the power of minus 14 meter. Then this uncertainty in the momentum comes out to be 1.1 into 10 to the power of minus 20 kg meter per second. Now, naturally, the momentum should be of the almost of the same order of the uncertainty in the momentum. That is, if the uncertainty in the momentum is 1.1 into 10 to the power of minus 20, then the momentum will also be of the same order. So we have the electron with the momentum in the nucleus 1.1 into 10 to the power of minus 20 kg meter per second. Now this much of momentum will have kinetic energy many times greater than the rest mass of the electron. And hence, for the kinetic energy of the electron, we will use the formula of the relativity, that is T is equal to Pc. So P we have 1.1 into 10 to the power of minus 20 kg meter per second, and C is equal to 3 into 10 to the power of 8 meter per second, the speed of light. Then the kinetic energy of the electron, if it resides inside the nucleus, will be approximately 20 million electron volt. We know it for sure. No electron has ever been observed to have this kinetic energy of 20 million electron volt. Therefore, our very presumption that electron could reside inside the nucleus was not tenable. Hence, electron does not belong to the nucleus. That is the conclusion we have. Then the next question, does the electron belong to the atom? And in the same way we have to proceed. Let us take the radius of the first Bohr example, first Bohr radius, for example, that is 5 into 10 to the power of minus 11 meter. This is naturally the uncertainty in the position of the electron in the atom will be of this order only, 5 into 10 to the power of minus 11 meter. So if we take delta x is equal to this much, then delta p correspondingly by same relation, delta x delta p greater than equal to h cross, the delta p will come out to be 2.2 into 10 to the power of minus 24 kg meter per second. Naturally, an electron with this momentum, now we have uncertainty in the momentum this much. So momentum will also be approximately of the same order of like this one. And if the electron is having this much of momentum, then this much of momentum is non-relativistic. And hence, the kinetic energy of electron can be calculated by simple mechanics formula, that is T is equal to P square by twice m. And it will come out to be approximately 17 electron volt. The kinetic energy of the electrons observed is of this order only. And we know that most of the electrons that we observe in our experiments are having energy of couple of electron volts.